Good afternoon, everyone. This is Zong from Zhejiang University. Today, I'm going to present ChunkGraph, an IO-efficient chunk-based graph representation model. Graph can effectively represent the relationships between entities, making it widely applicable in many areas. The real-world graph data has grown to terabytes, challenging the storage and analysis of the large-scale data sets. There are many different solutions to support large graph processing. Using large in-memory system or distributed system is common, but they are relatively expensive. Meanwhile, using large storage devices on a single machine offers a cost-effective solution. Currently, there are two main approaches: dedicated out-of-core graph systems and general-purpose memory storage cache system. We focus on these two solutions. The out-of-core systems are developed on a subgraph-based iterative model. They partition the whole graph into several disjoint parts and process each subgraph in an iterative manner. In each iteration, the subgraphs are sequentially loaded from disk into memory. For instance, when accessing vertex 1 and 3, subgraphs G0 and G1 are loaded and computed respectively. This method benefits from merging multiple random I/O into a single sequential I/O operation. However, there are three problems with this model. First, it suffers from low I/O efficiency because each access requires loading the entire subgraph. Second, it introduces extra computing overhead due to synchronization between subgraphs. Third, it's too complicated for users to implement their own algorithm because they always have to consider I/O management during coding. An alternative solution is to use memory storage cache-based systems. It utilizes page cache mechanism to manage data between memory and external storage. For instance, we store the graph in the CSR format and put the H data on disk. When accessing vertex 1 and 3, it loaded 3 pages from disk to memory. Compared to out-of-core graph systems, cache systems provide fine-grained access and show better I/O efficiency for sparse access. However, memory storage cache subsystems also have limitations. The first problem is the mismatch between page granularity and vertex access. Assume that we are using 4 kilobyte page. We can see the vertex degree varies. For example, for real-world data size Yahoo, over half of the vertices have only 1 or 2 neighbors, resulting in poor I/O efficiency for pages. And for high-degree vertices, they require too many pages, bring tremendous metadata overhead. This inspires us to adopt different storage strategies for them. Another problem is vertex cutting. It occurs when a vertex smaller than a page is split across 2 adjacent pages. For example, when accessing vertex 3 and 5, both of them need to load extra page, which could have been avoided. This inspires us to optimize data layout to minimize page accesses. Based on the above observations, we designed an IO-efficient chunk-based graph representation model, ChunkGraph. It features 3 key technologies: classified and hierarchical vertex storage, chunk layout optimization based on vertex reordering and combination, and differential chunk access. The first technique is the hierarchical vertex storage. We classify all vertices into 3 categories according to their degree. For many vertices, we directly store them in the index to avoid storage and addressing overhead. For medium vertices, we store them in chunks and avoid the cutting problem. For super vertices, we manage them using the huge page technique to reduce the page table entry and TLB overhead. The question is, for medium vertex, how to determine the appropriate chunk size? We implement hierarchical structure between the basic page and the huge page. Here's the example. We use 4 layers to accommodate different medium vertices according to their degree. The principle is always try to use smaller chunks to improve I/O efficiency. We also set buffer in DRAM for each layer and set the buffer size according to the chunk layer size. The second technique targets to optimize the layout of vertices. For some specific algorithm, if a vertex is accessed, its neighbor or sibling vertices are likely to be accessed in the next iteration. For example, if we run brand first search on the below graph. It takes 4 iterations to complete the algorithm, and if we arrange the vertices according to their ID, the page size is relatively random between iterations. And if we change the layout according to the topological information, the page sizes show better locality and I/O efficiency. However, this arrangement may left many internal fragments in chunks. To reduce internal fragments, we use complementary vertices to fill the fragmented chunk online. Finally, we get more compacted chunks, and that improves I/O efficiency. Our experiments show the number of chunks with fragments decrease significantly in our datasets. The third technique concerns about different access patterns for graph algorithm in the modern system. Top-down pattern assess parts of the graph, while bottom-up pattern scan all vertices to find activity parts. In this pattern, the vertex access order is different from the reordering order. This results in random access to each state when traversing all vertices, affecting the optimization effect of the chunk layout. Therefore, for the bottom-up pattern, we maintain key-value pair to record the mapping between the reordering ID and the original ID, so then we can access the edge state according to the actual vertex order in the chunk. That avoids random vertex access due to reorder layout. ChunkGraph is implemented based on Lagrange graph interface, vertex map, and edge map. It's easy for users to implement their own algorithm. Our ChunkGraph engine manages I/O between memory and disk, and is totally transparent to users. Next is the evaluation. We use a server with 2 sockets, each with 24 physical cores and equipped with 108 GB DRAM. We evaluated our system use 4 real-world graphs and 2 symmetric graphs. We use 2 different systems as baseline. Blade is a SOTA out-of-core system. Lagrange map is a Lagrange variant using mmap to leverage page cache to cache graph data. We evaluate to test ChunkGraph query performance and 2 other benchmarks, I/O overhead and computation overhead. Let's see the experiment results. We first compare the query time cost for our systems on 6 query algorithms. In general, ChunkGraph outperforms both Blade and Lagrange map, particularly for sparsely accessed graph algorithms such as BFS, single-sorted paths, SSP, and BC. We further measure the I/O overhead during the query process. Compared to Blade and Lagrange map, ChunkGraph shows better I/O efficiency due to their hierarchical structure and optimization on chunk layout. Meanwhile, we quantify computation overhead for different systems. ChunkGraph achieves similar computation costs to Lagrange map and significantly reduced overhead compared to Blade, as it avoids extra synchronization overhead. Here comes the conclusion. ChunkGraph is an I/O efficient external graph system for processing large-scale graphs, which mainly consists of 3 techniques: the hierarchical vertex storage strategy, chunk layout optimization based on vertex reordering and combination, and differentially assessed optimization. More evaluation results and analysis are in the paper. We are also published our source code in GitHub. Thanks for your attention, and I'm looking forward to ask you any question you ask.